Hey everyone! Today, we're diving into one of the hottest topics in machine learning, diffusion models. We'll first understand what they are, how they work, and then we'll code one from scratch using PyTorch. So, let's get started. Diffusion models are a type of generative model, much like GANs, generative adversarial networks, or VAEs, variational autoencoders, but with a twist. Instead of learning to create data in one shot, diffusion models take a more gradual approach. They start with pure noise similar to the static on an old TV and then slowly transform it into a meaningful image over several steps. This unique approach is what sets diffusion models apart. At their core, diffusion models are generative models. This means they are designed to generate data that is similar to the data on which they are trained. But what really makes diffusion models intriguing is the process by which they generate this data. This process has two stages. Forward process, also called diffusion. You start with real data, say, an image, and add small amounts of noise step by step, x1, xt, until it becomes pure noise, xt. Reverse process, also called denoising. You train a neural network to reverse this process, starting from noise and at each step, removing a little noise until you reconstruct something meaningful, like a cat, a dog, or a landscape. At its core, a diffusion model learns how to remove noise. It doesn't generate an image all at once, it slowly sculpts the noise into an image. Now, let's quickly peek into the architecture. Typically, diffusion models use a UNet architecture. UNet is great because it captures both local and global features, super important for images. At every time step, the model gets the current noisy image. It also knows the current time step because noise at different stages looks different. And it tries to predict the noise present in the image. So technically, the model's job is simple. Given a noisy image at time t, predict the noise that was added. Then, we can subtract that predicted noise and slowly move back to a clean image. Cool, right? This gradual denoising is the key to how diffusion models generate realistic images. A diffusion model is trained by finding the reverse Markov transitions that maximize the likelihood of the training data. In simpler terms, the model learns how to reverse the noising process to recover the original data. In practice, training involves minimizing the variational upper bound on the negative log likelihood, which essentially ensures the model is learning to denoise as accurately as possible. Now, let's dive into the code and see how this all works in PyTorch. I'll walk you through it step by step. First, we import PyTorch, matplotlib, and a few utilities. Nothing crazy here, just our usual setup. In diffusion models, at each step, we add a tiny bit of noise. The amount of noise added is controlled by a schedule, usually linearly increasing from small to large values. In the code, we define a beta schedule, from 0.0001 to 0.02 over 1,000 steps. Next up, we define how to add noise. The q_sample function takes a real image and a time step and mixes in noise based on the pre-computed beta values. The farther along the timeline, the noisier the image gets. Now we build our model. To keep it simple, we use a tiny neural network here. In real-world applications like DAL-E2 or Imagen, however, you'd typically use a much more complex architecture, such as a deep UNet, due to the high dimensionality and complexity of the data involved. While our simplified loss function seeks to train a model epsilon theta, we haven't yet defined the architecture of this model. The key requirement for the model is that its input and output dimensionalities must be identical. This constraint is why image diffusion models are often implemented using UNet-like architectures, which are specifically designed for image processing tasks where the input and output dimensions are the same. However, for simplicity, we'll stick to a basic feed-forward neural network that learns to predict the noise at each step. This feed-forward network will take noisy images as input and predict the noise that needs to be removed at each step of the diffusion process. But here, a basic feed-forward model learns to predict the noise at each step. The training loop looks very much like standard PyTorch. Pick a batch of images. Randomly choose time steps. Add noise according to that time step. Ask the model to predict the noise. Compare predicted noise versus actual noise. Compute loss and backpropagate. Finally, the fun part, generating new images. We start with pure random noise and run the model in reverse. At each step, we predict the noise. Remove the predicted noise. Add a little bit of new noise, optional for randomness. And repeat. This is how we create brand new images from scratch. And that's it. You've just built and trained your own diffusion model. Today we learned how diffusion models add and remove noise, how a small network can learn to predict noise, and how we can reverse diffusion to create images from noise. Until next time, keep learning and keep building.